Hey class, in order to help a little bit with your understanding of mesh analysis, I thought I would post a little video explaining an example from figure 216 that was posted in the notes. Mesh analysis, again, is a combination of Krukow's node and loop laws. It's just a quicker way to solve problems, and it's the way I prefer. In order to do it for this problem, first thing we need to do is for every box in the problem, define a current going through that loop or box. And in this problem you can see there's kind of two boxes, and so for each area we're going to define a new current. For example, we have, let's say, IA in this first box and IB both going clockwise through each mesh or each box. And then once we define those, now all we have to do is do Kirchhoff's Kirchhoff's loop law by assuming these currents. Okay, for example, if we start at point A, and you can really start anywhere, for this first box, what we're going to do is go around the loop in a clockwise fashion following IA. So first is if we start at A and move down, first thing we do is go across the resistor. Now, a resistor, every time you encounter resistance, it consumes voltage, so it'll be a voltage drop. And so we know we're going to lose voltage, so we'll say minus R1. Now you have to multiply it by the current that's going through R1. The current actually going through R1 is a combination of IA and IB. We don't really know the real direction right now, and so we have to take the combination of the two. And what you do is you say, well, IA is going in the same direction as my arrow, and so I'm going to start with IA, and then you subtract IB. Then if we continue, there's nothing happening until we get across this voltage, and because we've gone from a low to a high voltage from the voltage source, we increase in voltage, so we add plus Vs, and we get back to our beginning point, so we're done, so we say equals 0. Now if we start at A again for the next loop, we're going to move across here, nothing happens, and then we get across this resistance R2. Again, resistors are voltage drops, so we say minus R2. Only current IB is going through it, so we multiply that by IB. Then we continue around, and now we're going to go back the other way through R1 to get back to A. So, again, voltage drop R1, and now because we've gone up, we're in the same direction as IB. We start with IB, and then subtract IA, set that equal to 0. If you're ever confused on which one should go first, IA or IB, a rule is if you encounter in the same equation another IA or another IB, if you did it right, they should be the same sign. For example, can you see here that this IB is going to be a negative because of minus R2 IB, and the other IB is minus as well, because it's a minus R1 IB. So because of the same sign, that's a good check to make sure that I set it up correctly. And as discussed in the notes, if you continue to solve this, you can see that we get the solution posted in the notes, which will eventually give us IA and IB. IA equaling R1 plus R2 over R1 times R2 times the voltage source, and IB equaling the source over R2. And if the problem instead wants to know what is I1 and I2 instead of IA and IB, well, I2 is going through R2 and IB is the only current going through R2, so we know that I2 is IB, which we've solved as source over R2. Now the trouble is I1 is the difference between IA and IB, and the trick is to figure out which one goes first. Is it IA minus IB or IB minus IA? What you can see is I1 is in the same direction as IA, and so we'll put that one first. So I1 is really IA minus IB, and those are calculated here. So once you plug in those values and simplify, you'll actually have the solution for I2 and I1, really thick one. Alright, hope that helps. Maybe a little visual description of the example problem.